Displaying data from multiple tables. I'm really very excited about the content we're getting into in this nugget because it really takes what we've learned thus far by using the select statement and puts it on an entirely different plane. We're going to learn all about joins in this nugget. Joins are a topic that tend to scare off many newcomers to relational database systems, and SQL in particular, but I'm going to walk you through it as straightforwardly as I can, such that by the end of this nugget, you'll be able to pull exactly the data you want among multiple joined tables. We're going to learn, and we're going to start with the most common type of join, the Equijoin or inner join. We'll then look at outer joins, what those are used for. They do have a specialized purpose. You can even join a table to itself, if you can believe it, by using SelfJoin syntax. Then we'll use a somewhat less used technique, less useful, to generate what's called a Cartesian product, where you grab all rows, or all selected rows, should I say, from multiple tables. Let's get started. Importance of joins. Thus far in the course, we've been using the select statement to pull one or more rows from a single target table. Now that works just fine all day long, no problem. The same syntax rules apply, ANSI ISO or Oracle specific extensions, no muss, no fuss, no greasy aftertaste. However, as you become a little bit more proficient with SQL and have clearer ideas of the types of data, the columns that you want to pull back, you're going to find yourself very limited by staying within a single table. Let's look at this example I've cooked up for us on this whiteboard. We first have a small table, let's just call this DEPT for departments, that consists of two columns. A primary key column called Department ID, I'm going to put PK to represent that. Now we haven't formally covered column constraints yet in this course. For now, take it on faith that the primary key constraint ensures that every row in a given table is unique. That is to say, in this department table, there's one and only one department ID of 100, and that corresponds to the department name called prod. Same go with 200, 300, and 400. Now then, let's move to the second example. This is a table that we'll call EMP to store employee information. And again, we have a primary key constraint column called employee ID, or actually EMP ID, where we have a unique identifier for every row in this table to make sure we avoid duplication. Recall that avoiding duplication, avoiding redundancy to use a more formal term, is one of the key components of the relational database system or schema. Now, besides EMP ID, we're also tracking first name and last name. No big surprise there. Employees are going to have a first name and a last name after all. And we're also in the employee table going to want to track the department that each employee is a part of. Now you'll notice here that I'm using a column called Dept ID that happens to match the primary key column in the department table, although it does not have to. I personally like to match the column names exactly just so I have a clear idea of what's going on. And you'll notice that in Dept ID, we're using ID numbers that exist in the department table. Now why not just create a column called department and actually plug in the department for each employee? For instance, Pat Conroy looks like he or she is in the IT department. How about Chris Chi? It looks like that person is in prod. Tracy Malone looks like she or he, again this is an androgynous name by design, is in IT. Now some folks do that in their database tables. That's fine. They just put as much information as they can into each table. That begins to violate some of the rules of normalization, as we've talked about thus far. Normalization refers to looking at repeating patterns and looking for redundant data within a table column and pulling that out into a separate table. There's so many important reasons for doing that. You see that we're going to have multiple instances of IT staff members, multiple instances of sales people. Why not just, as I've done, create a separate table to track those departments and then reference the departments by their primary key ID field? Now when you do this, when you set up a matching column on a target table, you apply another constraint that we'll talk about later in the course, and that's called a foreign key constraint. In a nutshell, what's going on is this. We'll recall that in the department table, Dept ID has the primary key constraint such that there's only one instance of each of those IDs in that source table. By contrast, when that column is created on the foreign key side, we have what's called a one-to-many relationship, just by definition. As I said, here's two people who belong to the IT department, and it looks like Ann and Tom both belong to sales. So there's no constraint that says you can only have one dept ID in the employee table. This constitutes the relationship between those tables. That matching columns that may or may not have the same name, as I said earlier, these columns do have to share the same data type. That is important. The name isn't so important, the data type is. And then finally, we bind the primary key constraint on the one side of the relationship and the foreign key constraint on the many side of the relationship. And at that point, you've got the grist, so to speak, or the foundation for building a join. Now, I'm building up kind of slowly here to this bottom query result you're seeing at the bottom part of this whiteboard. Step back for a minute and just imagine we wanted to run a query to get first names, last names, and department names from our employee pool in our database. If we were limited to just one table selects like we've been doing thus far in the course, then we could query the department table, which is going to give us department names but nothing else. Or we could query the employee table and say select first name, comma, last name, comma, well, what else do we have here but department ID? And that query result would come back every day, no problem. But I don't think you, your colleagues, your boss, whoever, is going to appreciate seeing the names along with these ID values. People are going to say, well, yeah, this isn't very useful. What does ID 200 mean? What does ID 400 mean? We want the actual department names, which are now broken out into a separate table. No problem, though, because we have this relationship established between the two tables. We now can use join syntax to transparently query across both of those tables. We can pick and choose whichever columns we want across both of these tables, so we can easily get first name, comma, last name, comma, department name. I hope that in a admittedly long-winded way, I made my point and showed you how wonderful joins are with a relational database system. It's really what makes a relational database work. This concept of related tables and then using join syntax to pull the columns you want across those multiple tables. By far the most common type of join is what's called the Equijoin. Now, Equijoin is one of those Oracle geek terms. We know by now that in terms of the structured query language, we have the formal international standard defined by ANSI ISO, and then each database manufacturer, whether it's IBM or Microsoft or Oracle, will extend SQL to suit their specific needs. Well, in Oracle SQL, the Equijoin is equivalent to what's called the inner join in most other platforms. And we're going to see throughout this nugget that you can choose whichever flavor of syntax you prefer. Now, please note, for your SQL Fundamentals exam, you're going to need to be familiar with both syntaxes. That is to say, both the Oracle syntax for joins as well as the ANSI ISO SQL syntax for joins. But once you knock over your exam and you're actually working as a database administrator or database developer, I would encourage you to choose one of the two and stick with it consistently. Now, you may not have a choice. You may be working in an Oracle shop whose standard mandates one or the other. Personally, if you do have a choice, I would definitely recommend you choose the ANSI ISO for the simple reason that by mastering that syntax, you can port your SQL much more easily to other relational database management systems that, of course, are going to support ANSI ISO join syntax as well. Now, specifically, what the heck is an Equijoin? Equa should make you think of equality, and that is the root of the Equijoin or inner join. What we're doing is grabbing or selecting, to use the more formal term, one or more columns from two or more related tables that have a value equality in one or more matching columns. And what you see on the right is a representation of a Venn diagram. Venn diagrams are useful for logical things like joins. They're also used in psychology, interestingly enough. But what you see here, and we've actually done this in the previous whiteboard, we had the department table on one side and we had the employee table on the other. And what joined or linked those two tables was that matching dept ID column that you'll remember. So when we run our select In an equijoin or inner join fashion, we're relying upon matches between department ID values on the left side of the relationship as well as on the right side of the relationship. For this reason, ANSI ISO calls these inner joins. Now let's take a look at some examples of equijoin syntax. This first example uses the Oracle syntax, which I think on its face is intended to be a more straightforward syntax because it uses keywords that we're already familiar with. To wit, we have select and from, obviously, and we're basically inferring the join in our where clause. So let's see what's going on. We're selecting first name, last name, and department name from, and then here's another kicker. We're specifying more than one target table using a comma-separated format. Now, the order of those tables is unimportant in an equijoin. As we get into outer joins, it is significant which table you list first. But because an equijoin, you'll remember, matches on a common column, it really is 6 in one, half dozen in the other, so to speak, whether you list table 1 first or second, etc. I also want you to see we're using table aliasing. This should not be a surprise to you. So our employee or emp table we're aliasing to E, and our department table we're aliasing to D. You're going to find almost universally, friends, as you look in the literature, not just for Oracle, but any RDBMS, that when you get into join syntax, in order to keep your tables and your columns as compact and easy to read as possible, you'll find that it's almost a given that you'll want to alias the table names, because otherwise, if we weren't using aliasing, our select statement would read select emp.fn, emp.ln, dept.department name. And when you think, well, I've already chosen pretty compact table names here, but some table names are pretty honkin' large and makes readability an issue. So anyway, our select statement grabs transparently the columns from all indicated tables that we need. And then in Oracle Equijoin syntax, we just specify in our where clause where employee department ID equals department ID. Simple as that. It's really straightforward and compact syntax. The disadvantage, as you see in my comment, is that it's blocking up your where clause. What if you had where filtering to do on this query? It's not going to work when you use Oracle Equijoin syntax here because we've already consumed our where, you see? Let's take a look at ANSI ISO format. We have the same exact query, but you'll notice the syntax is just a little bit different. We've got our select line, that's exactly the same. Our from statement is almost the same. Instead of a comma that we use in Oracle syntax, we use inner join. So we have our table 1, inner join, table 2, and then what we're doing here is we're employing a new keyword. We haven't used this one yet. It's called using. And using allows us to pass in one column that will be the matching column between the related tables. Now this is fine. It's again a nice tight compact syntax. But what if your tables had different column names? That is to say, what if our department and our employee tables on that matching column, let's say it was called DID for department ID over here, and then in the employee table, our foreign key, the many side of the relationship, we called it dept ID. Well, this syntax is going to fail in that case because those matching columns have different names. Now remember, best practice, use the same name as well as the same data type, and that way you can employ the using syntax all day long. But you need to be aware of all three of these variants. The using mechanism is cool because you then have a full open where clause to do row level filtering. Finally, our second variant on ANSI ISO Equijoin syntax, first two lines are exactly the same, but instead of using the using clause, we can specify on. Now, in my experience, this is what I tend to gravitate toward just on a daily basis. I'd be interested to know what your thoughts are on that. But what's nice about the on syntax is that it opens up the where clause, and it also gives us the ability to have the matching column have a different name. So we just specify on, and then I use parens. You don't have to, but I want to be as explicit as possible, and then specify the exact name, table.column name, for each of those columns indicated in the join. Pretty straightforward, I hope? Well, if you understand the equijoin or the inner join, congratulations, because you're at least 75% there to any practical use of joins in the real world. The other main join type that's going to comprise, I would say, 24.5% of the remaining percentage, with self-joins and Cartesian products taking up the rest, is the outer join. Now let's look at these Venn diagrams. In these examples, I guess this is green and I guess this is blue. If my colors are incorrect, please forgive me. I happen to be extremely colorblind. But let's take the green to be our department table and the blue or violet or whatever it is to be our employee table. There may be cases where you need to see all of the rows on one side of that table relationship and only ones that match on your key field, your primary key foreign key field, on the other side. So the Venn diagram shows an overlap situation. On the left here, you're seeing a representation of what's called a left join or a left outer join. On the right, you're noticing the overlap is the employee side. That's the right join or the right outer join. Now, how does that work in practice? Well, what you're seeing down below in the whiteboard is the department table. I've added some additional rows, as you see. We go all the way up to ID 600. And then on the right, we have our employee table set up with that related column, just like we had before. And then down at the bottom, we have the result of a left join or a left outer join combination. So what we're seeing here are not only the rows that match, in other words, on the right side, these department IDs, 100, 200, 300, and 400 match what are in the department ID tables. That constitutes the conditions for an inner join. But when you specify a left outer join, we're going to grab everything from the left side of that join syntax. So in this case, we're going to see additional rows come back in our query that list those additional department names. Oracle will substitute null for any other columns because, of course, in a left outer join, in the case of maintenance and marketing, ID 500 and 600, they don't appear on the right side of the relationship. Now, this is a very practical way to go. I probably should have adjusted that split a little bit. I was a little bit flippant when I said that inner joins comprise 75% of what you'll use in the real world and outer joins 24%. Just take that with a grain of salt. Outer joins can be very, very helpful indeed. If you want to look at all employees that don't have a department name associated with them, actually this shows you department names that have no employees associated with them. So outer joins are not just some intellectual exercise. There are many cases where you're going to want to use them in a real-life fashion. Now let's take a look at outer join syntax. The two varieties of outer joins are left outer join and right outer join. There's what's called a full outer join that's outside the scope of this course. We're going to concentrate on left and right. Now, whereas with an Equijoin, you didn't have to worry about the order in which you listed your related tables. Here, as I told you earlier, of course, just logically, it's going to make sense. The order that you put those tables in is going to tell Oracle which is your left and which is your right. Now, the first instance I'm giving you here is the ANSI ISO syntax. The second is Oracle. And actually, what I just said about the order of the tables isn't as important with Oracle syntax as you'll see in just a moment. First, let's have a look at ANSI ISO. Our select line, no big surprise there. Our from line, instead of using inner join to link those two tables, we're specifying either left outer join or right outer join. And then we can use the on syntax to map the appropriate columns together. Pretty similar stuff. Bottom line is if you understand inner join syntax, you understand outer join. The toughest part is just conceptualizing in your mind what you want to see in order to determine which type of join fits that problem. Oracle syntax is a little bit wonky. Check this out. Again, we're using a very compact from line where we're just doing a comma-separated list of those tables. Order absolutely matters, remember. And then with Oracle syntax, we do our join on the where line. And what's happening here, it's kind of interesting. You use the plus operator to denote or tell Oracle whether it's a right or left outer join. So in this case, we're displaying a right outer join. So we have department ID equals employee department ID plus. So if we wanted a left outer join, we would just move this paren plus paren over here after the d.department ID. Kind of clever, isn't it? It's actually a little bit old-fashioned in my opinion, but it works. Lastly, let's take a look at a less useful technique called generating a Cartesian product from two or more related tables. What we've got here in ANSI syntax is what's called a cross-join. And the reason why Cartesian products or cross-joins are rarely useful in the real world is that they grab all rows irrespective of the match between those tables. You can essentially take any two tables and run a Cartesian product or cross-join against them, and you wind up with literally a product. Table A's rows times table B's rows. Now that's different. That is to say, the cross-join is different from a full outer join. Remember I mentioned when we looked at outer joins, the ones we're concentrating on are the left outer and right outer. There's a third outer join type available to us in Oracle called full outer join that is not A times B, where you've got table A's rows times table B generating a product, but you have table A's rows plus table B's. Essentially, conceptually and logically, it's a left outer join plus a right outer join. A lot of folks confuse the cross join and the full outer join, but they are distinct. A self join is actually a lot more useful than you might think. In a self join, you're joining a table to itself virtually. Of course, there's one base table involved, but you're simulating a multi-table join syntax. Self joins are really useful for us in the real world for detecting data inconsistencies and troubleshooting. Now, if you see our example here, let's look at our fictional employee table that includes, in this case, 3 columns: employee ID, employee name, and manager name. You'll note we have an implicit one-to-many relationship. Now, you may be thinking along the lines, why didn't we take this manager column and break it out into an additional table? And you'd be perfectly right to say that. However, in the real world, full normalization isn't always going to be what you see. So in this case, because the managers exist in the table themselves, I mean, here's Collins, and Collins exists as an employee, you have an internal relationship inherent. So check this out. We can see all employees and their managers by selecting emp name. I'm aliasing that column to staffer, and then emp name aliasing to manager. And I'm prefixing those table aliases or virtual table aliases as E1 and E2. So just imagine in your mind taking the same table and duplicating it. So we're aliasing one instance as E1 and one as E2. And that's what we specify in the from clause. You're referencing the same table using inner join syntax with different aliases. And we're matching on our match column the manager name column to the emp ID column. Better correct this manager name reference there. Something like a self-join is best seen in a demo. So why don't we head out into Oracle and take a look at all of these different join types in practice. In this demonstration, we'll work with table joins in Oracle. Now don't be thrown off by the user interface. Perhaps you didn't even notice it, but sure enough, I'm working with a Windows Server 2008 R2 machine on which I've installed Oracle Database 11g R2 and of course SQL Developer. Everything is the same data-wise from my Linux machine. I just wanted to switch over to Windows to demonstrate the point that these tools and all of the statements we're learning in this course are completely platform agnostic. Now then, you see that I'm logged into SQL Developer. I'm logged into our database as the HR user, no big surprise there, and we're going to start this consideration of joins by running describe against a couple key tables. We're going to look at employees and departments from the HR schema. First, let's run describe on departments and take a look at its setup. It's a fairly small table. You see that there are just 4 columns. Our department ID column, which I will just tell you is the primary key column for this particular table, department name, and then there's actually a couple foreign keys that go to other tables, managers and locations respectively. However, for our purposes right now, I want to draw your attention only to the department ID column, and I want you to notice its data type is number 4. So if we now mosey on over to employees and run a metadata check on it, let me increase the screen a little bit. We have a primary key column called employee ID, first name, last name, blah, blah, blah. Let's go all the way down to the bottom, and sure enough, we have a matching column here called department ID, and it uses the number 4 data type. Now, you may very well be thinking very logically, now Tim, how do you know that employee employee ID is a primary key? How do you know that department ID here in employees is a foreign key? How do you get that kind of metadata? And the answer that I have for you, friends, is twofold. You can get that metadata using SQL or directly within our first or third-party management tools. I'm not sure where we left off here, so I'm just going to do my best. With respect to gaining constraint data on a given table, the two ways to go about that in Oracle are: one, using commands like describe and select on select data dictionary views, or number two, you can use a first-party or third-party tool. Of course, SQL Developer is a first-party tool. Now, why is this important? Well, as I just said, for us to gain metadata to figure out where or which columns specifically have the primary key and foreign key constraints respectively on those two tables, employees and departments, we can, for instance, run a describe on user_constraints. This is the data dictionary view that gives us an insight into constraints on objects that we own. And we've been working, as you know, just as a reminder, in the HR schema. If we select everything from user constraints, we see a pretty overwhelming list. We can cut that down quite a bit by just filtering on certain columns and then throwing in a where clause where table name equals departments, for instance. And this gives us the name of the constraint that's built into that table, the constraint type, whether it's a primary key or a foreign key. You'll notice department ID PK is the name of the primary key constraint that's attached to the departments table. Once you know the name of a particular primary key constraint, you can determine its column within a table by querying user cons columns, yet another data dictionary view. Now, I don't want to get too far off track with this discussion of constraints. It just fits in well with our current work on joining tables, because underneath the elements that tie tables together in a relational fashion are these constraints known as the primary key constraint and the foreign key constraint. Now again, we can dig around here until we find department ID, and there it is, and it tells us the column position and so forth, which column has that particular constraint attached to it. That's all well and good. I've found, and this is just my own experience speaking, coming from primarily a background in SQL Server, it's a lot easier to look at table structures in that platform than it is with Oracle, especially when you start having to go into using SQL to query column information and constraint information. You wind up having to write several lines of code, often involving joins on multiple data dictionary views to see what you want. It's actually, I find it quite frustrating. By contrast, we can use first or third-party tools to look at constraint information. In fact, SQL Developer is pretty good in that regard. You'll notice here I have the connections window exposed. This is my current connection, and we can expand the tables node to see only the tables that we own that are in our schema. And for instance, there's departments. If we give that a double click and then hide our connections pane, we see the results of a describe statement. It gives us more than running describe from a SQL prompt. We've seen this view before. By double-clicking the table, we can look at the column structure, the data itself, and then, of course, constraints. Tells you exactly what's going on inside that table. All this stuff is well and good, but it's really academic to our current consideration, which is the join. So let's scroll down a little bit and take a look at what we've got going on. To set the stage, let's run a basic select statement against individual tables and see what we have. Selecting employee ID, last name, and department ID from employees yields the following result. If we want to see what those department IDs mean, without joins, we would have to query the departments table separately. And there we can see the department ID primary key value and then the unique piece of data that gives us the name. Now, if we want to, for instance, to see employee ID, their last name, and the department name, as you know, we're going to have to involve some join syntax. And the most common type of join, as we know, is the inner join or the Equijoin. Notice here on line 22 in my from statement that according to ANSI ISO rules, because I think the inner join is the de facto join type, you don't even need to include the word inner. I can just say join, and it's implied that we're talking about an Equijoin or an inner join. Now, I like to be as explicit as possible, so I'm going to throw inner in there. However, I wanted to show you that, strictly speaking, just join will work as well. And in this particular example, starting on line 21, we're employing the using syntax that assumes that our match column, our primary key / foreign key column, has the same name, department ID, and we're going to order those results by employee ID. So let's select those rows and run the query, and here we have it. We have our rows back in ascending order by employee ID, where we have each employee's last name from the employees table and their respective department names from the join departments table. Pretty easy, right? Now, remember, the other ANSI ISO way to draw these joins is to use the on keyword. Here we have the same query. Actually, it's the identical query. Again, I'm going to throw in inner here just for completeness. But instead of employing the using keyword, we're using on, which you'll remember is especially useful when your matching columns do not have the same name. But we should find that the results of this query return the same rows, as you see they just did. Now, with respect to self-joins, let's take a look at what we've got in the employees table here. Let's select employee ID, last name, and manager ID. Now, what we have here is quite a bit of repetition. Because employee ID is the primary key column in this table, there's not going to be any repetition there. Potentially, there could be repetition with last name. But when we think of a self-join, you were thinking of recursiveness. That is to say, we have managers indicated in this table in an internal one-to-many relationship. That is to say, you'll see Kochar's manager is ID 100. Now, who is ID 100? We don't have to go to another table for that information. It's actually looked up in the local table. Kochar's boss is King. Hunold, his or her boss, is ID 102, and that happens to be Dahan. So when you have this internal recursion, this is a good candidate for a self-join situation. An example of which we have here beginning on line 39. Remember that when we do an internal or self-join, you're creating two virtual instances of the same table. So on line 40, we're referencing from employees and then doing an inner join to the employees table itself. The second instance, I'm aliasing to M to denote that this is the manager, or we're focusing, I should say, on the manager ID column. So it looks like we want E.lastname, and we're aliasing that as employee. That's coming from the left side of the relationship. And then M.lastname, aliased as manager, coming from the other virtual instance of that table. The key to the self-join isn't just the duplication of the table name, but it's the on keyword here, where we specify which columns are matching. And here we're taking the manager ID from one side of the relationship, and we're matching those numbers to employee IDs on the other side. Exactly what I showed you a couple minutes ago, where we referenced Kochar, his or her manager being 100. And how do we map that? Well, we map it to employee ID 100, which is King. So this query from line 38 to 42 is going to give us a nice run of employees and their manager's last name, called a self-join. Line 48 is a more complex example, perhaps goes a little bit outside the scope of what you'll be expected to know for your exam, but the purpose of this query is to just demonstrate that you can join more than two tables. And you can not only join more than two tables, but you can have more than one join condition. So in this case, we're selecting employee ID, department name, city, and state from three different tables. Notice the alias prefix, E dot, D dot, and L dot. Our first join is this clause here, where we're doing an inner join between the employees table and the departments table on that matching key field. No big surprise there. And then we're adding in a third table join, locations, that's matching between the location column in the departments table and the locations table, you see? So you can just simply run your joins sequentially. Select these rows, run it, and we get our results back. Here, this is just giving us a really wide swath of information where we're pulling employees' ID numbers. Now, we could, if we wanted to, add additional columns to our select statement, maybe E.firstname, E.lastname if we wanted more rich information. But in this report, we have the employee ID, the name, not ID of their department, their city, and their state. Really useful information, all given to us by virtue of the join. You'll recall that we have two outer join types, actually 3 if we count the full outer join, the left outer join, the right outer join, and the full outer join. On line 56, we have an example of a left outer join. Here we're looking, we'll jump right down to 59, at the employees table being on the left side of the join and the departments table being on the right. So we're grabbing first name and last name from the employees table and department name from the departments table. And we're specifying, again, the order is crucial here. Employees on the left, departments on the right, on the matching key field, and then we're doing an order. So let's select these rows and run. And if we scroll down to, in the results, line 39 or row 39, we have a Kimberly Grant. And you'll notice that this individual does not have a department name associated with her. Remember I mentioned that self-joins and then to a degree outer joins can be useful for capturing anomalies. In this case, because the employees are on the left side of the left outer join, we're not only getting results based on the matching column, in other words, where a department ID exists in both the employees and the departments table, but in this left outer join example, we're also getting all of the employees regardless of whether they have a department ID associated with them. So therefore, Kimberly Grant shows up in this list, and due to some clerical error, evidently, we don't have a department name associated with that user, you see? Good example of the left outer join and its utility. Same thing applies for the right outer join. On line 63, we have the same query formulated in opposition, where this time, on the right side, we're going to return department names that don't have any employees in them. So let's select these rows, run the query, and if we scroll through the results, we will see a whole bunch of department names for which Oracle substituted nulls for first name and last name. So the first 100-something odd rows have that match between both sides of the join on department ID. In other words, there's an employee with an associated department name. The right outer join gets you all the outliers here, as you see from line or row 107 all the way down to 122, where we have literally nobody in those departments. The full outer join, which is brought to the forefront with the full outer join syntax, is, as I mentioned earlier, different from a Cartesian product in as much as it's the equivalent of running a left outer join plus a right outer join. So therefore, we should expect to find not only our Kimberly Grant row, let me scroll down and find her. Yep, there's Kimberly Grant. She came in from the left outer join run, but we should also, if we scroll down to the bottom of the output, again, see our right outer join results, our department names that do not have any associated employees inside them. The final example we'll look at in this demo starts on line 77, and this is the ANSI ISO CrossJoin, also called the Cartesian product in Oracle literature. The syntax here is pretty straightforward. We are, irrespective of a matching key column, simply specifying column names and then running two tables together. So in this case, we're specifying first name, last name, and department name, and we know by now that first name and last name come from employees, department name comes from departments. You'll notice that I'm not prefixing these columns with a table name. So there'll be a question here on both of our lips, I think, and that is, can Oracle successfully resolve those column names? And then the Cartesian product is simply taking the one table and combining it with the results of the second table. Let's select these rows and run the query. And as I scroll through the results here, they're absolutely huge. Almost 3,000 rows came back, and notice that there are no nulls. Let me run the full outer join one more time, and by comparison, there were only the 123 rows. So this demonstrates experientially that the cross join and the full outer join are very different constructs. Displaying data from multiple tables review. We covered a lot of good material in this nugget, and I hope you're quite satisfied with your progress thus far. At this point, you should understand the basic mechanics of the inner join, also called the Equijoin, the outer join, the self-join, and the Cartesian product, which we know is called a cross join. You should be familiar with both the Oracle as well as the ANSI ISO syntax for these joins, because you're likely to see one or the other or both on your live exam. We'll be continuing to build on our join syntax familiarity as we proceed through the rest of the course. I hope that this has been informative for you, and I'd like to thank you for viewing.